Hello, my name is Emery Hill, and I will be presenting my Physics 2 lab on electric charge. To start with our introduction, the purpose of the experiment was to effectively use Coulomb's law to calculate the electric charge between two charged pieces of tape, one floating above the other. In doing this, a computational model was created to make calculations and visualize the situation. For a quick preview of our main results, the image on the left is the computational visualization of the pieces of tape represented as spheres and the forces exerted on them. Below, those numbers are the numerical results of the charge required for the tape to float and the percentage of the atoms that lost electrons. Behind this, there's a lot of physics at work, including Coulomb's law, which states that electrically charged objects create electric fields around them, and that these electrically charged objects have attractive and repulsive electric forces based on their charge and field. Down here is the formula for Coulomb's law. There's also Newton's second law at work, which is very important for calculating our gravitational force on the top piece of tape, and then of course vector magnitude unit vector formulas. So to start with our models and software, we use GlowScript coding in Python to create the visualization. And just as a quick breakdown here, you can see the spheres are the pieces of tape. The orange force is the normal force on the bottom piece of tape for my hands. The yellow is the gravitational force on the top piece of tape. And then the green vectors are the electric forces. And here's a better representation of what actually happened with our system surroundings and initial conditions. The system is the top piece of tape because that's what we're looking at most of the time. The surroundings, that's my hands, the bottom piece of tape, the air, anything else that could have interacted with it. To start with our initial conditions, the bottom piece of tape is at the origin 0, 0, 0, and the top piece of tape is above it by 0.002 meters. The length of both tape strands was 0.2 meters, and their width was 0.01905 meters. For the procedure, two pieces of tape were charged by separating them, kind of ripping them off another piece of tape very quickly. The height that one floated above the other due to electric charge was recorded at, it was 2 centimeters. The electric charge was calculated using Coulomb's law and the gravitational force on the top piece of tape. The net force was 0, they weren't moving, so we can set those equal to each other and calculate. Using the surface area on the tape and the atoms per meter squared, the number of atoms on the surface of the tape was calculated. And then using that number and the charge, the percent of total atoms that lost electrons from the tape during charging was calculated. And that calculation on the bottom there, that was my charge calculation, which I thought was the most important in the whole experiment. For the coding in GlowScript, we can break that down here. Initial variables are on 2 to 4, lines 2 to 4. Creating the tape particles was 6 through 10. Initializing the R vector between the tapes was 12 through 14. Calculating gravitational force on the top tape was 16. Calculating electric force was line 20. The visualization arrows is kind of the bulk of this with 23 through 37. And then calculating the percent of atoms that lost electrons was 39 through 46. You can pause if you want to look at any of the code closer. For the analysis of the whole experiment, the visualizations, calculations, and final numbers, they all supported each other. Because the model is completely based off the data we took and the physics principles, there's no major differences or discrepancies between the two. If the data is flawed, the computational model is flawed as well, but I do not believe it is. The only minor differences that really exist are the assumptions we made. Air resistance was ignored, the tapes were treated as point masses, and it was assumed that the charge was evenly distributed on them in real life. But besides that, the model and real life align completely. For some final questions, what if the electrons and protons charges were switched? Theoretically, this would change nothing because it didn't matter whether they were both positive or both negative, it just mattered that they had the same charge. As long as they both have the same charge, the tapes will still repel. And why handle the charged tapes carefully? Well, if they come in contact with another surface or object, there could be a transfer of electrons that could reduce the charge, and if it has a weak charge or no charge, the experiment will not work. For some potential errors, human error with the tape is always possible, as I just mentioned. And then measurement error, well, the tapes were moving, so it's not perfect where we're looking at on the ruler, but that's always possible. And then sign errors. If you mix up a negative or positive in the experiment, it could fundamentally change the whole thing. Thank you for watching.